So today's lecture is about optimization. Optimization's kind of fun because you get to use computer tools and play around with numbers. Anyway, when we sit down and what is this course about? It's about decision making. And we're all different, but we're systematic. And so this course is about getting you into that mindset of looking at data and looking at things numerically and quantitatively, that there's actually evidence that points you in one direction or another to make good decisions. And so the path through this course so far has been first about probability, because we need the tools to figure out how do we weigh things. And one of the biggest things to come out of probability was expected value, that the likelihood of something happening times the value of it is the value that we can expect out of it. Next, we talked about, a big part of making decisions, the first part is, what's the likelihood of my course I'm picking is going to happen? But then what's going to be my payoff? And so that payoff is about risk benefit. So we talked about how people do weigh benefits. The next part is games. Every part of a decision essentially comes down to a games. And there are specific kind of games that exist that pretty much express themselves in business or in life or warfare or whatever. And next, what we're going to talk about is optimization, meaning, given all this data and everything, how do we find the best solution? I love the word optimal, because optimal means that you've made all the trade-offs and there is a path to go forward. Not only that, but things form patterns, and so they form networks. And so the question is, how do we get the most out of that? And finally, we end up with machine learning. And that's the algorithms and the processes that pretty much drive everything today. So today we're going to talk about backward induction, operations research, linear programming, structured data, and I have a question mark next to that, and you'll see why, and also integer programming. Now, what do I mean by backward induction? Say I want to buy an airplane ticket with American, JetBlue, and Southwest, and this is how much it costs. And this is actually the real cost of tickets. Everybody thinks Southwest is the cheapest, and they're not. So what should I buy? What are my options? Well, if I go or don't go, so for Southwest, the nice thing about them is that your plane ticket is still a credit, and so you can use it, but you have to pay, the difference in fees. JetBlue, same thing. However, with JetBlue, the base fee is going to be less. American, on the other hand, you have the opportunity to buy insurance. So when you have these big problems like this, what you need to do is just have the patience to write out every scenario. And so if I buy insurance or don't buy insurance, what's next? Am I going to go or don't go? So I'm saying I have an 80% chance of going or 20% of not going. And so you see with American, you're taking a very big risk. If you don't go, then you lose the original price of the ticket and their change fees and everything else. On the other hand, if you buy insurance, it's much less. However, this is what I mean by backward induction. Typically, you look at the end result, but besides the end result, you also look at the interim results. And the reason why you look at the interim results is because that's what you're actually going to be paying before you've actually gone. So you can see what the upfront costs are. Why do you want to look at games in each of these kind of steps? You want to look at it in all these steps for the simple reason that if you know the value at each step and how it changes when you go to the next step, then maybe you change that step. It's an indicator of what step you want to go to. But instead of spending a lot of time going through it, you typically go backwards. And that's why backward induction is so useful, because you already know what kind of outcome you want. So you go backwards. And instead of using trees, sometimes trees are harder to manipulate. You could put it into tables like I have here. I love spreadsheets because if you don't like the result, what do? You start playing around with the numbers. For example, will you go or won't you go? Well, what's the best case that I'm going to go? What's the worst case I'm going to go? Maybe I need to improve the odds that I will go. And so you see how values change, and also buying insurance or not buying insurance. Now, in terms of, and so that's the last aspect of games I wanted to talk about. And so that's the wrap up. Operations research is a field right now that's about making analytical decisions and better decisions. And where did it all start? World War II. And so when they were trying to figure out where's the optimal pattern of sticking radar, or where should we stick mines in shipping lanes, and one of the big pioneers in this area was actually MIT. Actually, World War II kind of made MIT because they got a boatload of money. But why am I interested in operations research? And it's because it helps me make sense of data. It allows me to simplify things. And that's that if I have too many options, too many things to consider, and too much uncertainty, how do I go about making good choices? I need to find a way to simplify it. And through this analysis, we develop processes and skills, and that makes up our toolbox. Common focus areas that are used in operations research is you're looking at networks, meaning how different entities are all connected, how people respond in business, science, and engineering. These are the areas that use data the most. The paradigm of doing these problems is first I have decision variables. Those are my knobs I can turn. The objective function is ultimately what is it that I want to get. And there's constraints. Variables can't be infinite. I'm never going to solve it. So how do I pare it down? And for a lot of these, we have a non-negativity constraint, and that means it's got to be greater than 0. So when you're talking about something physical, no, you can have a negative amount of steel. Well, I suppose you can. You can owe steel to somebody, but you know what I mean when you're trying to build something. So let's look at this problem. Supposing a company's building different stones or tiles. They make less money on stones versus tiles, but it takes a lot less time to make stones. So what's the optimal mix of this? I'm building stuff for 90 days. What I find out is that it's unfeasible for me to make 100 tiles. So what's the optimal mix? And so what I do is I think about how many days, the profit, and the quantity. And so what are my constraints? My constraints are how much time I have. Based on the number of stone tiles I make, it's a half S plus T. Has to be less than 90 because it's 90 days. And what's my objective? To make as much money as possible. So my profit is equal to the number of stones that I have times $1 plus $3 times the number of tiles that I actually make. And so that's what I'm trying to optimize. I'm trying to figure out what's the quantity, how much money is it going to make, the profit, and how much time is it going to take. And so what ends up happening is there's a tool in Excel. Now, some of you will have this in Excel, some of you won't. The way to download it into Excel is there's an add-in feature. You use the add-in feature to download Solver. And so this is one of the requirements of this class. How does Solver work? Well, I set my objective function. So on my spreadsheet, it's the cell that gives me profit. And I want to maximize it. What cells do I want to change? The number. It's these two quantities that I want to change. And here's my total profit. And I can express that as a sum. Next is, what are the constraints? And so here's all the constraints that we talked about. And here's the non-zero constraints. So the quantities, the total time it takes, the profit, and everything else. And so these functions are pretty much self-explanatory. I want to add a line. I want to change a line. I want to delete a line. And I want to use a linear model for this. And then I hit solve, and it figures out what numbers I actually need. And so when I get an answer, it tells me the original value and what the final value is. So you put in dummy values, and it turns out that I should spend all 90 days making tiles. Also, when I look at the constraints, some variables matter, some variables don't matter, or a limiting effect. For example, if I say t is greater than 3 and t is greater than 5, well, t greater than 5 is just redundant because t greater than 3 will cover everything that t greater than 5 is going to cover. And that's what it means by non-binding. It doesn't really have an effect on the outcome. If I just take a simple algebraic example where I have 17x plus 20y, and then I have all these constraints. I have coefficients, it optimizes it, what x should be, what y should be, non-zero constraints. And so these limits on the constraints is referred to as the right-hand side. And my objective function is this. This is what I want to maximize or minimize. And then I need some kind of starting values for x and y. So this is a way. Now, you can set up your spreadsheets any way you want. This is just the way I do it. And so, again, here's an example of solver of how to set that up based on what I showed previously. And here are the results that come out. So the final value that's optimal is 3 and 6. Now there's something called sensitivity table. What is the usefulness of sensitivity tables? It tells you there's more than one solution that actually exists. What these optimizers try to do is the space of all solutions, it tries to pick the middle point. Now we'll see that middle point actually has certain connotations to it, what they actually mean by middle. But what this means is how much can I increase the value or decrease the value and still come out with the same answer. What a shadow price means is that if I increase driving variables by a specific unit, so in this case it'd be changing these by 1. In this case, it's this constant 1. If I increase it by 1, how much does the total value increase or how much does it decrease? And so, as we see there. And if I say 1e30, it just means it doesn't matter. If I have a solution and I don't like the solution, like maybe I want to make more out of it or something like that, you can change the right-hand side, you can change your objective coefficients, and your sensitivity gives you information. So those are the things that drive an optimization algorithm. So once again, here we have the sensitivities, and it tells you, as you can see, there's a lot of 1e30s, a lot of don't cares. And once again, there's also nonlinear sensitivities for functions that aren't linear. And so what they do is they look at gradients because you can only look at it over a small finite space. So in terms of simulation, again, if I don't like the result, I can change the cost coefficient, I can change the right-hand side, or I can make a totally new product, which has totally different variables to it. Here's the types of programs. Linear is most common. There's also nonlinear functions and elements, and those get a little trickier. And there's also integers, absolute values. Now, what about risk return? Risk return is another example that you optimize. And so what's my objective variable? My objective variable is I want to minimize the variance. Because if I'm an investor, it's about risk reward. And so my bias now, you can maximize rate of return, but odds are variance is going to be very high. And we don't like variance because that's uncertainty. We want surety. We want a sure thing. What you can do in these models is actually minimize the total variance of how it's added together or balance out the variance and come up with your own expression of variance and rate of return, like you can do it as a ratio. Here's another example of optimization to go into a little bit more detail. That investors use optimization, and what they try to do is balance off risk return. The way they determine what to optimize is called the Sharpe ratio, and that's the return divided by the variance, or I should say standard deviation. So P means my portfolio. This is my expected return minus, and this is the risk-free rate. This is the real growth. One thing they talk about, the growth in our economy, they're saying, oh, it's 4%, it's 5%, this is all record. Well, no, it isn't. And the reason why it isn't is because inflation is at 2%. So the real growth is only like 2%, which is in line with what's been going on for the last decade. Anyway, so the constraints are, I have two stocks, A and B. And so I decide to weight it, which I'm calling omega A and omega B. So since these are being weighted, they have to equal to 1. And the standard deviation is given by this. Now, we have a correlation coefficient between these two. And so what rho AB refers to is actually the correlation between these two stocks. So what Dr. Cho did is actually came up with data for Target, Apple, and Facebook. Which two of these stocks do you want? So here's the return, the R's, and here's the variances. And here's the inherent ratios that they have. Now the Apple one was actually much higher, but then you would never buy Apple stock compared to the other two. The weight is what we're interested in. And so we have 3 different cases, 3 different combinations of stocks. These are just the dummy numbers. And I just did this as an example for the first one. This is the correlation coefficient. And where did I get this? I got it from the data. And figured out what the correlation, Excel figured it out for me. So the R, the sigma squared. Sigma is just the square root of sigma squared. The risk-free rate, I'm assuming, is 2%. And so the Sharpe ratio comes out to this. So when I look at the Sharpe ratio for all 3 opportunities, as it turns out, Apple, Facebook, Target, Facebook are about the same. But this is the least of the 3. So how did I solve that? Solver. So what am I trying to maximize? I'm trying to maximize my Sharpe ratio. And so these are the conditions. And essentially all these just have to be greater than 0. And I also, though, in terms of picking out values for this, has to be greater than 0. But this one has to be less than or equal to 1. I don't need to do it for this one. It's because this is equal to 1 minus whatever this value is. And so I have no need of it. Now, because these have lots of squared and things, terms like that, it's nonlinear. So I had to use a nonlinear model. But then I hit solve, and that's how I came up with this. So it's the same kind of problem, and it's a lot easier problem than flowing widget A, B, C, and everything else around it. But this is the basic idea behind stock optimization. In terms of how these algorithms actually work to get optimization, you could do it by geometry, actually. And geometry shows you the operating regions, the optimal solutions. We'll go through this. And the methods for doing this are called the geometric method and the simplex method. And that also gives you the sensitivity analysis. So for example, what if I have these equations and constraints? What ends up happening is I start drawing lines for the constraints. And if you remember basic geometry from like algebra or whatever, and remember it's like if this is greater than and this is less than and everything, and they all overlap in a certain area. That's the solution space. So how do I find the optimal space? Well, that area creates what's called the feasibility region. That's the solution within the constraints. And so the optimal solution actually ends up at one of these corner points. So what I do is once I plot out what the geometry looks at, I go to every corner point and just see which gives me the highest value. And that's what we mean by the center of the solution. And as you could see, I calculated this out. You could see what has the highest value. And so as it turns out, it's this 1.67 times 1.33. So this number here, and that gives me 7.33. That's the optimal solution. So convex sets means that considering I have these geometries, I'm concerned about whether or not I can actually draw lines to have a well-defined space. And so a convex set means that if I draw 2 points and draw a line there, every point on that line is going to be within the closed set. Is that convex? Yeah, it is. Because if you sit down and think about anywhere where you put 2 points, you could draw a line through it. Is this convex? No, it's not. And the reason why is because if you put points at the corners on these loops, you connect the line and yeah, you're not in the space. Is this convex? Yes. Pretty much any polygon is going to be convex. What you're looking for is the void points within it. And so obviously this is not convex. The simplex method is actually the linear algebra approach to optimization. And what this does is, and this is what actually the Excel program can do, and it's because computers can do it, is that once you have all these intersections, you have vertice points. And so what they do is they actually go from vertice to vertice and figure out what the outcome is until they get the right answer. Now, combinatorial problems means that you can have more than one combination of things. And so an input is data for an instance in the problem. And an instance means just one specific case. Feasible solutions come from whether or not the decision variables are feasible. And objective functions is for every value of x, there's an associative objective of x. And so the goal is to find that x that minimizes the error. Some other problems that we look at in optimization has to do with networks. And what a network is that I have different elements and those elements are connected. So those elements are referred to as nodes. They could be people, they could be cities, they could even be markets. As long as they're a well-defined entity, and so the question is, how are they connected? The traveling salesman problem is pretty classic, and that's that I have to return to the point I start from, and I have to hit every point. And so where's the minimum path through this? Where's the minimum pattern? And the minimum pattern, you probably already guessed it, goes like this. Now, you can go in different directions, and you can do it in different ways, but you're not going to get less than that. You can also do it with numbers. Supposing I have a part of the sequence of numbers, and I want to minimize half the numbers minus the other half. Which numbers would I pick? And actually, there are programs that will optimize this for you. So the minimum I could possibly get out of this is 1. And I probably should have an absolute value around that. And so examples of what this is used for, supposing you have a network. And so what's the feasible solution set if everybody has to be connected? And so I want the most possible. Integer programming means that I'm looking for feasible solutions, but I want them to be integers. And so I don't get these middle points. When we look at certain problems, traveling salesman is a combinatorial problem because there are all these different combinations I can have of segments. And this is what we mean by combinatorial problems. But I'm trying to optimize that. Integer programming, when you sit down and think about it, is I have all these different integers that could be combinations. So it's a combinatorial optimization problem. The whole key is, how do I optimize that function? So isn't this all just linear programming with a different kind of constraint? And yeah, that's pretty much what integer programming is. Nonlinear functions aren't necessarily just second order whatever. They can also be impulse functions like this. Integer programming is basically I'm adding the constraint where it's got to be integer valued. One way of doing it is maybe I'm going to define everything within 0 to 1, that it's pure integer programs are greater than 0. There are integer programs which you can have which are 0 or 1, which are digital programs. And then I can have mixed programs where I can have an integer for everything. But the way I would do an integer program, and here's an example, here's my line that defines everything. Well, all of these are integers in here. So all these are within the solution space, so how do I pick it? And so what I would do is I would actually have to go along each of these line points and figure out which gives me the highest value. Here's a problem to work on, and I will post the solution online, but it'll give you some practice in using Excel.